Okay, let's begin. So, the next major topic we want to do is work, but I think I also want to talk to you before we get there. Let's kick this dog as we walk by. Talk about hyperbolic trig functions. So this is just going to be a new class of functions that we want to talk about. That could be useful, and they'll pop up every now and then, depending on where you are. They might pop up in multivariable or differential equations. They just show up every now and then, and sometimes it's convenient to use them. So we are going to learn about these new kinds of functions, and basically just learn how to do calculus with them, what they are, that sort of thing. And it might help us out in the future. So they're called trig functions because they're developed in sort of the same way that trig functions were developed. They are meant to measure the coordinates along, instead of a circle, they are measuring the distance along the unit hyperbola. So remember, trig functions just measure the coordinates along the unit circle. If instead we want to measure coordinates along the unit hyperbola, which is that equation, turns out the coordinates here is going to be given by functions that we call Cinch and Cosh. Actually, it's the other way around. No, sorry. Where x is going to be the angle here. Okay. Now, as you can see, they're measuring something that looks a lot like the unit circle, so we get a lot of equations that look much like the unit circle, like what you see with other trig functions, which is why they're called hyperbolic trig functions. And we have the following definitions, which you can derive this based on this setup, but we're not going to because it's just going to take too long. We can derive that we can measure the height at any point, called Cosh. So this is called, let me write it down there. It's defined as e to the x plus e to the minus x all over 2. This is called the hyperbolic cosine. Kind of like cosine, but the hyperbolic case, not the circular case. Or we will refer to it as just Cosh. Okay. So the other one is called Cinch, the hyperbolic sine. Referred to it as Cinch. So these are the two main functions here that measure the coordinates, and we also defined the others, like what we call the tanh, the hyperbolic tangent. This is going to be Cinch over Cosh. We can define the hyperbolic secant, which is 1 over Cosh. We can define the hyperbolic cosecant, which is 1 over Cinch. We can define the hyperbolic cotangent, which is 1 over Tanh, or Cosh over Cinch. Now once we define all these rules, it turns out that we'll get a bunch of equations that are very similar to ones that we remember from the trig functions. So we'll have our own list of Pythagorean identities, quote unquote, but they're not really going to look like the Pythagorean identities because they have they'll have negative signs or positive signs in somewhat unexpected places. But let's look at some of those. What do I want to talk about? Maybe the graphs. Now, graphs. So if we look at the cosh graph, y equals cosh. In the same way, yes, it's measuring a coordinate along a hyperbola, but if you track that one coordinate by itself, what would the graph actually look like? It actually looks almost like a parabola, but it's hyperbolic. It increases faster than a parabola. So its minimum point will be at 1, and it will increase based on the exponential over 2. So we would have something like, if you look at that graph, e to the x over 2, and you look at this graph, e to the minus x over 2, and the cosh is adding these two, so his graph is going to look like the sum of these things. It'll be asymptotic to that guy, so it looks like a parabola. And if you look at the cinch, so the blue is not a part of the graph, just the black is the graph. The cinch, well, first you look at the e to the x over 2, and we're going to minus e to the x over 2. Minus e to the minus x over 2. And so you're taking the blue curve minus the bottom blue curve, and this guy ends up looking like this. So as it goes off to negative infinity, it will be asymptotic to this one. As it goes off to positive infinity, it will be asymptotic to that one. So it sort of looks like a cubic. The tangent graph actually looks like an inverse tangent. Look at y equals tangent. The upper bound is going to be 1, the lower bound is going to be minus 1, and it looks like. So those are the pictures. Now, using the exponential definitions, we can derive some important formulas. So just have an idea of how the graphs look. Identities. Well, note if you take cosh squared x and subtract sinh squared x, what you would have is e to the x plus e to the minus x over 2 squared minus e to the x minus e to the minus x all over 2 squared. This is going to be e to the 2x plus 2 plus e to the minus 2x all over 4 minus e to the 2x minus 2 plus e to the minus 2x over 4 and then what you would notice is going to happen is that these guys would get subtracted. We have a plus 2 minus a minus 2, so this ends up being plus 4 over 4, which is 1. And so it also works out that this actually does look like the x squared minus y squared equals 1. So this gives cos squared x minus sinh squared x equals 1. That's That's an important identity. The following are derived similarly. I don't want to spend too much time on it though. So we have things like, if I divide this through by the cosh, we would end up with 1 minus tench equals the hyperbolic secant. So instead of the 1 plus tangent squared equals secant squared, you have 1 minus tench equals secant. And what are other identities that I want you to know? I mean, we could divide by the cinch instead, and we have the hyperbolic cotangent divided by 1 equals the hyperbolic cosecant squared. There's no any other identities. It turns out that they also have addition formulas, so if you look at the cinch of say x plus y, it's going to look very similar to the sine of x plus y. It's cinch x cosh y plus cinch y cosh x. You would also notice that if you take the cosh of x plus y, it actually keeps the sign, so this would have cosh x cosh y plus, so that's different from the addition form for cosine, cinch x cinch y. Another thing you would look at, and you're going to see why these are, they can be convenient. Another one. The cinch is an odd function. You can see that from the graph as well. So if you look at the cinch of a negative value is the negative of cinch, and the cosh of a negative value is just the original value. So cinch is odd, cosh is even. Any other identities I want to tell you about? I don't think so. That's probably it. Let's move on. Let's look at some calculus with these guys. If you wanted to differentiate, say, the cosh, you realize that this is just the derivative of e to the x plus e to the minus x all over 2. Well, that's just going to be e to the x minus e to the minus x all over 2. That's your cinch. So this means that if you differentiate the cosh, you get a cinch as opposed to negative cinch. So that's an important rule. Similarly, we can derive the fact that the derivative of the cinch is going to be the cosh. We can derive that the derivative of the tanh is going to be the hyperbolic secant squared. It's going to look very similar to the trig functions. The thing you have to worry about here is that every now and then the signs are going to be in weird locations. So you're used to seeing 1 plus tangent squared give you secant squared, whereas here it's minus. So every now and then the sign is going to flip on you. Just be aware of that. But the fact that the sign flips on you is actually something that's quite convenient, which we'll get to. The other one, so if we have the cosecant, the secant, and the cotangent hyperbolic look very similar to trig functions, but all the reciprocal hyperbolic trig functions carry a negative sign with them. And so the cosecant, the derivative of cosecant, is cosecant cotangent, and this behaves similarly with the hyperbolic version. And the derivative of secant is secant tangent. This actually behaves similarly with the hyperbolic version, and this is going to be minus cosecant. So you can just go to the exponential definitions and you can actually derive these. I'm not going to do that. Let's talk about so I looked at the definitions. They measured the coordinates on the hyperbola. We looked at the graphs, the identities. We looked at how to differentiate them. Maybe we want to look at the inverses. Okay, so we have that. Oh no, I actually did some examples first. Let's actually do that. Just to get a break and actually do something. Find y prime. It's been forever since we just did pure differentiation. Without like needing it in a part of an integration, but just play around with these a little bit. Has everyone seen hyperbolic function before? It's like your first time, because I'm really rushing through it. But the truth is, you don't need to know. It's not like, oh God, if you don't know them. Right? But they can be useful in a pinch, and there are times when they'll just pop up randomly out of nowhere, and if you recognize them, it'll be good for you. As well as they have some specific applications where they're nice, although I can't say a lot of people actually use them that way. The rare engineer will use these functions a lot. Derivative. Yeah.
Would it just be 2x sine hx squared?
Yeah, just the chain rule. So as long as you remember all the derivative rules over here, and you remember things like the chain rule, the product rule, the quotient rule, all that stuff, it's just applying that here. So x cubed minus 3 times Cinch. How would we find the derivative here? Product rule. So you're going to differentiate the first thing, leave the second thing, plus leave the first thing, differentiate the second thing. y equals Cinch. Derivative of Cinch is the hyperbolic secant squared. But because it's not just x, you have to multiply by the derivative of the inside. 1 over x. So in this case, you have a division here, so part of the quotient rule is what you're going to want to do. It's the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Don't think that really simplifies to anything. And finally, find the derivative of this. Derivative of ln of anything is the derivative of the thing over the thing itself. So that is Cinch. What else? This. Let's talk about their inverses. Now these you might find particularly useful because the inverses have these forms that ordinarily we would want to like use maybe like a partial fractions or a trig sub to figure out, but with these guys we can actually just not do any of that. That's cool. So let's actually figure so for the cosine, the cosh, hyperbolic cosine, we do have to restrict the domain to be able to find the inverse, because you need to be 1-to-1 and onto to find an inverse. But we can define inverse functions. So if x equals the sinh of y, we write y equals sinh inverse of x, and similarly, if x equals the cosh of y, we write y equals the cosh inverse of x, and vice versa. So we can define inverse functions for these guys, and more importantly, let's look at the calculus with the inverse functions. Let's say I actually wanted to find a derivative of, suppose y was equal to the inverse cosine what is y prime. So here's something you can do to figure that out. And so I'm just going to derive one of them for you and then just write down the forms for the other one. Here's what you can do. You can set x equals cosh of y, and then differentiate both sides. So basically do implicit differentiation. Derivative of x is going to be 1. Derivative of the cosh is going to be y prime times the sinh. So this means that your y prime is going to be 1 over the sinh. And this means that your y prime is going to be 1 over, well, because I know that cosh squared, cosh squared x minus sinh squared x is 1. This means that cosh squared x minus 1 equals sinh squared x. And so I can take the radical of the cosh squared x minus 1 equals, to get the sinh. And so this becomes the radical and we can ignore the negative sign because of how the cosh behaves, it's positive, so cosh squared x minus 1, y. But the cosh y was x. So we get 1 over the radical of x squared minus 1. And so what we have here is the following. This means that the derivative of the inverse cosh is going to be 1 over the square root of x squared minus 1. And a nice thing for us in Calc 2, this also means, via the fundamental theorem of calculus, that if I were to integrate something that looks like 1 over the radical of x squared minus 1 dx, now prior to just now, had we seen that and we wanted to integrate it, we would have to like do a trig sub. We would set x equals like a secant of theta, and you'd go through that whole thing and blah blah blah. But now we can just say, oh, that's actually the inverse hyperbolic cosine. You can just do that. That's just like straight from the definition at this point. And so little things like that make these guys very nice to deal with. Not the most common things in the world, but whenever they show up, they do kind of make your life a little bit easier. Or sometimes, even if it's not just making it easier, sometimes you have some sort of expression where it's nice to actually use it with a trig function, but the sign is just off. Like there's a negative sign where you wanted a positive sign. A lot of the times a hyperbolic trig function will actually be fine with the negative sign. The others are derived similarly. How many did I do? All 6 of them? I did do all 6, but I wouldn't ask you to memorize all of them because even I don't memorize all of them, we don't use them that often. So, for example, the derivative of the inverse sinh, that is going to look like 1 plus u squared, derived pretty much the same way. The derivative of the inverse tanh, that's going to look like 1 minus x squared. And the derivative of, do you want to write these down? I'll just write them down. ask you to memorize it, but at this point it might be a nice bonus problem to like ask you to derive something like this, and you just go back to the kind of things we've been doing before, either the definition or inverse secant. But things like the inverse tangent is very nice, because as you can see here, 1 over 1 minus x squared is something that you would kind of assume pops up all the time. Now, if we had to integrate something like that, if we had the 1 over 1 plus x squared, we know that that's automatically the inverse tangent if we integrate that. But if you have 1 minus x squared, then you're now, oh, we have to do partial fractions and you get 2 ln's and blah, blah, blah. Or you can just say the integral of this is going to be the inverse tangent. This is going to be negative u times the radical of 1 minus u. I was writing down the chain rule versions, but I'm giving you the regular versions here. X minus x squared and the derivative the cotangent hyperbolic. Few more examples, then we move on. So I don't really want to dwell on these guys. I'm basically just giving you a few new tools to put in your toolbox. If you're ever in a situation where you can take advantage of them, do so. Y prime. You guys try those and then we'll actually move on. That was the crash course in hyperbolic functions. That's it. Pretty much the main things I want you guys to take away is that, we have a bunch of derivative rules and integration rules that can be of advantage when we're in certain situations that would be annoying otherwise, because we'd have to use like a trig sub or partial fractions or just be messy to deal with otherwise. These guys can come in handy. Do you guys have your work handouts? I gave you last time. That's the thing I want to get to, but we're going to do it right after these. Okay, what are we gonna do here? The derivative of sinh 3x. What's that gonna look like?
3 over the square root of 1 plus 9x squared.
Mm-hmm. Yes. E. The derivative of x squared is the cosh inverse of x. Yeah.
2x cosh inverse plus x squared over square root x squared minus 1.
Yep. Next one, y equals the tanh inverse of x squared plus 1. What's that one gonna be?
I think it's 1 over
Mhm.
1 minus, in parentheses, the square root of x squared plus 1 squared. But that
Right,
would,
so
well,
that's
that would
just
just
gonna
imply
be x
that
squared
1
plus
over,
1.
yeah. Times 1/2 times x squared plus 1 to the negative 1/2 times 2x.
Cancel. And the negative, the 1 minus the 1 is going to cancel, so I'll just have the negative, and this will be x squared. And here I would have x times x squared plus 1 to the minus 1/2. And the x would cancel. So that would look like minus 1 over x times the square root of x squared plus 1. Do you remember the rules to differentiate an exponential, a general exponential, like 5 to the something? So what was the rule? If you wanted to differentiate, so recall, if you want to differentiate a to the x, what does it look like? Right, a to the x ln of a. So d y equals 5 to the cosh inverse, then this means your y prime is going to be, well, 5 to the cosh inverse ln of 5 times just the chain rule. So now you're going to do the derivative of the cosh inverse, which is 1 over the radical of x squared minus 1. Ideas of integrating tanh.
Turning it into Cinch over cosh.
Then,
ln, or not ln, it's use of cosh.
right, u equals the cosh, your du is going to be the sinh, so you end up with 1 over u, you're going to integrate that, you're going to get the ln of u. So that, even though technically you don't need the absolute values here, the cosh is always positive. What about this one?
Tanh 1 minus e to the x.
Well, not the 1 minus. I mean, that would just be tanh
Oh, e to the x.
inverse of e to the x.
Right.
Right, so basically what you would have done is a u substitution. U equals e to the x, your du would be e to the x dx. So you end up with the integral of 1 over 1 minus u squared du. Now you could have done that, and ordinarily how we would have dealt with this is we would do partial fractions, change the denominator to 1 minus u times 1 plus u, split that into two things, the ln, and we get the ln of 1 minus u times some constant plus the ln of 1 plus u times some constant, but this is directly the tanh inverse of u for us now. So yeah, that is just that guy. Alright, finally it's time for you guys to do some work around here. The obligatory pun. That's the next section. We are going to do work. So this is an application of integrals that we're going to be looking at. We'll see, do we see many others? To physics. It's a very important application. Work is important. So let's talk about that. We'll spend a couple classes on this topic because even though there are very few ideas that we're working with, being able to apply these ideas in various situations, it can be somewhat of a challenge. So let's actually define what work is. Do I want to start with the definition or the units discussion? Maybe I'll start with definition. We define work. I'll just give you the equation definition as force times distance. So a force is, of course, a push, a pull, or a twist. If you apply the force to some object over some distance, you say you have done work on that object. So this force is applied to some object over some distance. Product of the force needed to move an object and the distance the object travels under the influence of this force. So, for example, a 10 pound weight is lifted vertically and placed vertically off the ground, let's say. So the example, just to illustrate the meaning of what we're saying. Lifted vertically off the ground and placed on a 2-foot table, then the work to move the weight is 10 times 2 foot-pounds. That's how we would state it, i.e. 20 foot-pounds. That's just an example. You just multiply the force. I'll talk about the units of force pretty soon, but pounds is a unit of force, feet is a unit of distance. You're applying a force of 10 pounds to lift the weight of 10 pounds because of, Newton's. It's either the first or the third. I can never remember the order of them. Newton's first or third law. So to actually lift a 10-pound weight, you have to actually apply 10 pounds of force to move it. And if you move it a distance of 2 feet, you say you've done 20 foot-pounds of work. You just made that multiplication. One thing you can note here, from this we can define just an equation. Well, what's up? Work equals force times distance whenever the force is constant. So that just falls straight from the definition of how we're looking at work. However, here's the issue, and here's where most of our time is going to be spent trying to figure things out. It is not always the case that constant force is being applied. Sometimes your force can vary. So constant force just means you're applying the same amount of force throughout the entire action. So how do you go about talking about when you have some variable force acting on an object? We are pretty much going to do a variable force acting on an object in a straight line. To actually act on an object in some sort of curve, we need multivariable calculus, and so we're not going to do that. We need the idea of a line integral. We're just going to do our old vanilla integral. So we can visualize work as an area. So that's how we're going to start the process. Basically, we just imagine if this whole force times distance thing is going to be how we're going to define it, then if I were to sketch force versus distance, And if I have some constant force, let's say it's moving from position A to position B, and my force is just a constant function. So this here is f of x equals the force, and it's constant. Then the work needed to apply this force over the distance between A and B is simply going to be the area under this constant function. So we are going to just extend this idea that if the force is not constant, we generalize this to non-constant forces. So if now we're tracking our force and it's actually changing, right? So here it was increasing, then we decrease the force, then we increase the force, then we decrease the force is actually moving. The same idea is actually going to be applied. If we're moving from position A to position B under the influence of a force that acts like this, we can calculate the work by essentially, you're going to take a bunch of force times distances, you're going to dissect this into that, you're going to get a Riemann sum, and basically you generalize this as just, the work is just going to be the area here. So f of x here is force. Which gives us a better definition of work than this one here. It's a very high school definition of work. Work is force times distance. A much better way to think of work is the integral of force. Work, which I'm calling W from now on, big W is just going to mean work, is equal to the integral of force. Let's call it f of x dx from A to B, where f of x is measuring force being applied to some object. Over the, it's not a time interval, it's a distance interval. So your x here is used as measuring the distance. So work is the integral of force. This is an important idea. And yeah, that brings us here at the end of the first paragraph. Okay. So yeah, work is just force times distance. Good thing about this is that we can think of it as an area, kind of a length times width, where the height is measured by the force and the distance is measured by the width. Yes?
Will we always be working with things that are being picked like directly straight up and not at an angle?
No, we are going to cover 3 particular situations, but yes, we are doing straight up, straight. So it's either going to be horizontal or vertical, but as you can see the subtopics here where you really want to cover 3 things. I want to show you how to deal with Hooke's law when it comes to forces. I want to show you how to deal with lifting or pulling problems, so we're lifting something off the ground or pulling something with a cable in a vertical fashion. And as well as we're going to look at pumping problems. So we have a tank with some liquid in it of some known density, and I want to know how much work is it going to take us to actually pump out the fluids. So we're going to look at very specific instances. To deal with things more generally, And now you're going to need to know about vectors, and because angles you have to measure it in terms of vectors, and now you get into vector calculus and line integrals, and yeah, we're sticking with straight up and down, working against gravity kinds of problems. Yes. So work is the integral of force. That's an idea that you can apply in general. It's just that integral can change based on context. The most general form is what's called a line integral, and that will take care of arbitrary directions. But for now, we're pretty much moving in straight lines. Important notes here. Is you're going to have to pay attention to the units in this section. So a lot of times we'll often, pretty much always, see work problems in the form of word problems. And the units will give important information. So, you should know based on the unit that you're reading what kind of thing that you're looking at. So, talk about units of force. I'm going to give you one, a pound. Pound is a unit of force, right? Pound or weight, as we might call it, is a unit of force. So whenever you see something that's 2 pounds, it's actually not measuring like the mass of something, it's measuring the force. Sometimes that is not understood. I don't think I'm going to give you any empirical units other than pounds. It's important to know that when you see pounds, it's actually measuring a force. So if something is measured in pounds, and you can come up with a formula to describe whatever thing is being measured in pounds, you can plug that straight into this formula and use that as the force function. But now you can have units of what we call mass. And these are like the grams and kilograms. So these are G, and this is called kg. Kg is the standard unit of mass. Length. The meter is a unit of length. Foot is a unit of length. And we tend to use meters with kg and pounds with feet. So you'll see that often happening. Those two ways of measuring things are going to be often the case. So a problem that's talking about measuring things in pounds, they're normally going to measure their distance in feet. Anything measured in grams or kilograms, they'll normally measure their distance in meters. So you're either doing empirical units or the standard scientific units. What else? When, this is important, when given a mass measured in grams, should convert to kilograms very usually. And multiply by the acting force, which for us pretty much always gravity. We're going to be acting against the force of gravity all the time. We're lifting things up and gravity is trying to pull them down. Now gravity is the force of attraction that we feel being pulled towards the center of the earth. The gravity, the force of gravity on earth averages at it's sometimes referred to as the acceleration due to gravity. Do you know what this is? Right. It's 9.81 meters per second, usually around to 9.8 is 9.8 meters per second squared. So that's when your distance is measured in meters. Do we know what it is in feet?
Times 3.
It's 32 feet per second squared. And it's usually considered negative, by the way. This is usually considered negative since it acts downwards. Okay. So we are in a situation, if I tell you, oh, there's this thing over here that's 10 kilograms. Don't use that 10 kilograms in the problem that you're working with. You have to take those 10 kilograms, you have to multiply by 9.8. And so you would actually use 998 in your calculations. So let's talk about when those units are put together. Now, we do this because of, I'm pretty sure this one is the second, Newton's second law. We know that force is equal to mass times acceleration. And so here, if m is going to be the mass, which is going to be a gram or a kilogram, a is going to be an acceleration, which is going to be the acceleration due to gravity. By multiplying these two, we obtain force. So it's very important when you're reading the problems, you might need to multiply by gravity. And when do you need to multiply by gravity? If I give you grams or kilograms. If I give you pounds, don't multiply by anything. Use the pounds. So that's going to be important. Now, the unit kilogram times meter per second squared. So here, when you take the unit of mass times the unit for acceleration here, you get a unit that we call, does anyone know what this is called? It's called a Newton. Big N for a Newton. You should capitalize that for whatever. But this is a unit. And it's a unit of force, because I just took a mass times acceleration. So this is actually a unit of force. unit of force. So if you're reading a word problem and newtons are mentioned, that thing that you just read is telling you a force. Oh, blah, blah, blah is 5 newtons. That 5 represents a force. So you should know that. Now, if we are measuring forces in newtons and distance in meters, so say I gave you a problem, oh, 5 kilograms, blah, blah, blah. You convert it to newtons, and then that's the force, but then you're going to apply the force times distance to get the work. To get work with this. So let's say you take the Newton, which is a unit of force, and you multiply that by, say, m, which is a unit of distance. You get what's called, this is called the Newton meter. Dash meter. I think he's deserving. And it might also be called, does anyone know another name for the Newton meter? It's called the joule. Called it Big J. Called the joule. That's also named after a person, but I don't think they capitalize that. Now, those of you who have done a lot of work with this, which I guess if you're in chemistry or physics and you've done that to any reasonable degree, you will notice that the joule is actually a unit of energy, which is not a coincidence. Work and energy have a very intimate connection. Energy is what we call the capacity to do work. So you have an object doing work, energy is what provides the fuel to that object to do work. So another way to think of work, which we're not really going to think of it that way, is it's a measure of a change in energy states. If you have something doing work, how much energy it had before doing that work and how much energy it had after, if you measure the distance in that, you can actually track how much work is being done by measuring the distance and difference in energy states. Yeah, when you do like multi-2, that's going to come up, and they're not going to tell you that that's going to come up. It's going to be stated as something called the fundamental theorem for line integrals. But yeah, it's basically saying that. Okay, so work is like energy. Oh, yeah. All right, so that's. I think that's all the preliminaries. Like once we can jump into examples. But yeah, it's very important that you pay attention to the units that we'll be reading. And I will see you guys next week.